Start recording, buddy. Okay. So what I was commenting on is that models are like maps. So, like all maps, they're imperfect. Like all maps, they're specific to purpose. What do I mean by that? What do I mean by the fact that a map is specific to purpose? Well, if we want to use maps for different purposes, we'll seek different things on a map. A map of Saskatoon that we'll use to figure out the best way to drive through the city will be quite different from a map that we'd use as engineers, electrical engineers, which is in my training, to figure out why there was a blackout last week within the city. We would seek, for a driving map, we'd seek to understand street connectivity, street maps. For a map associated with that blackout, we might seek to understand the electrical connectivity of the city. What mains are connected with what electrical transformers and what lines, and what are the voltages along the different lines, etc. Where are the step-down points? If we want to understand why flooding occurred downtown last summer, we might want a hydrological map, a map that shows the topography of the land and where water would flow, etc. Right? Different maps, different purposes. Are each of these maps a lie? First of all, are they perfect? Is anyone map perfect? No, no one map is perfect. Are the maps good despite being imperfect? Yes, they can be. Good for a particular purpose. And so it is with models. Models, like maps, are abstractions. Like all good maps, they leave out details. They allow you to focus on the details that are germane to your particular interests. And by leaving out those details, they eliminate clutter in those investigations. But they are imperfect, and they are to be used for particular purposes in mind. The abstraction might be rather different if you had different purposes in mind. So these models we work with have in many ways similarities with maps. And like a map, the only map that's perfect of the world is the world itself. And that isn't a very useful map. You can't put it in your car to navigate around the city. It doesn't fit. Right? Among other things, there's an issue with recursion there. How are you going to fit the map of your car into your car? It's a perfect map. But similarly with a simulation model, all of what we're going to be dealing with is abstractions. And in this case, ladies and gentlemen, the abstraction is particularly simple. We are representing personhood in all its fullness as a very simplistic sort of decomposition here. We divide people up into susceptible, infectious, and recovered categories, and we allow for progression between those categories in a very fixed way. Now, we're going to be actually modifying this model in a few minutes, a bit down the road, but right now we allow susceptible people to do what? What are the possibilities in life right now for people in this model? Susceptible people can get infected. They can get infected, or by implication they can stay susceptible, or they can get infected. Infected people can do what? Well, they can recover, and it turns out with this little arrow here on the right-hand side, they're going to be able to infect other people, okay, periodically. And so this is the dismal state of life in this model, is the depiction of personhood. We've abstracted people to have susceptible, infected, recovered, and they're associated with a color. Now, these individuals are further, it turns out, associated with some elements of context that aren't shown here. That's shown up in the place that captures context in the model, namely the so-called main class here, okay? And you'll notice if you double-click on main, you'll see some information that will be germane to the behavior we'll be seeing in a few minutes. But over here on the left, we'll see that there's this population of people. This is a population of individuals of a certain size within this model, as specified by the total population. And those individuals will have aspects of context dictated by this so-called environment here. That environment will tell them where they're located, to whom they're connected, in terms of adjacency, and to whom they're connected with networks. In this case, ladies and gentlemen, we are specifying that these individuals are laid out on a grid of 500 cells, as it were, by 500 cells, in a space of equal size. So each individual is a pixel, single dot, and they have a neighborhood type, which is known as a Moore neighborhood. And that means that agents are connected to neighbors on northwest, east, and south, the cardinal directions. And we've seen the natural history of infection. People start susceptible, and all but one person starts susceptible. That one person starts infected. And each individual abuts others in these cardinal directions, and they can be infected through those cardinal directions. So if there's a susceptible, they can be infected by someone who's in north, south, east, or west, and if it's an infected, they can pass the infection on to someone, just like you, sitting in your seats, arrayed before me, like agents, could spread your infection in a localized fashion. Okay, so we've talked about this some. Let's actually go try to run this model. Now, did I hear someone remote here asking questions? No? Okay. So let's go to this model. Enough of talk, and let's let the model speak for itself. So to run this, I'd like you to right-click on. Excuse me. I have a component you don't right now. So I'd like you to go right-click on simulation here, and I'd like you to select Run here. On Macs, it's a command click. I've forgotten. Another alternative is you could use this. You could select that experiment and use this button up here. Okay, to run it would be another alternative. Okay. So having done that, what we're going to be seeing is a screen come up like that. For those, because I know people are doing this out there for the first time, I'll just show you the other way. You can do this, and you can pick up this one here. Now I have other models open, so it gave me a profusion of possibilities that you won't have. Okay, so we run this, and this model is, ladies and gentlemen from computer science background, this model is a program. It's running. When I fired that up, what did it do? What would it need to do to turn that model into something that's runnable? Speak. Compile. It needs to compile it, and it needs to fire up, in this case, the Java virtual machine. This is a Java application, in fact. It's written in Java, and we'll see elements of Java speak to us today. It needed to compile it, it needed to build it, and actually even before that, it needed to turn it into Java, it turns out. Compile that, and then turn it into bytecode through the compilation, and then fire a Java virtual machine, for those for whom those are meaningful terms. So here's this model that came up, and I'm going to press this button to run the model. Now, when this runs the model, it's going to create the space that we saw depicted. And it's going to place a single index individual within this space. Okay. Now, one of the things I'd like you to do is I'd like you to go and take a look as this grows, and I'd like you to go down the lower part of the screen and select here in this little triangle pointing to right. I'd like you to select model time, so the model time is shown here. Now we see some behavior taking place here. What are we seeing?
I'm having a problem here with Java, saying that it doesn't support a 32-bit.
Oh, okay. So I suspect what's happening is it. I suspect any logic has one it's either 64-bit or 32-bit any logic, and probably the Java virtual machine is a different one, different type. What I'll suggest is that I can look at this after class, but for the moment, I'd like to suggest that you try to bind to one of the other students, if you can, or you can follow me on my screen, alternatively. But I know about this issue. Is this on Linux? Or is this on Mac? Okay. Yeah, so there is an assumption about the compatibility of the Java virtual machine, but normally AnyLogic comes with its own installation of Java. So I'd have to look at this after class, okay? But in the meantime, you can follow things on my screen. Okay, so here we're seeing the infection spread out over time. Can anyone describe roughly what's going on? What are we seeing?
Susceptibles are infectious and then time they are recovering.
Okay, so you'll notice, and thank you very much, that's quite right. We see susceptibles, as Kimmelpreet said, susceptibles are being infected over time, and over time they're recovering. You'll notice in the upper part of the screen here, there's color coding. And this is going to have a lot to do with that so-called color variable we saw earlier that labels each person's color. So we have susceptible in yellow, we have red denoting infectious, and we have this gray denoting recovered individuals. And each individual here are these little dots. And where's the action at? The action's at the places where there are infectious individuals. Why do we see this pattern? So we see a sort of semicircular pattern. Why? What's going on here?
Well, you start from considering perfect infection, i.e. that you're going to absolutely infect everyone around you instantaneously.
Yeah.
And from that, when you start with just one person, you infect every person around you in a circle.
Oh.
You know, everyone is tight against each other. It's not like we're sparse in this class. So you're going to see just, a circle growing bigger and bigger. However, that's deformed slightly because of that reduced chance of infection.
Okay, so this is interesting, and you're hitting a lot of things right on their head. Let me ask this. So you've sort of characterized why this behavior results from the, as it were, that we depicted in the model. Let me ask this: is this circle in our model somewhere? So where's the circle?
In the more property where they're all infected, when you put that on macro scale across the entire population, it winds up using the person in any direction. There's no in terms of what direction it goes.
Okay, so the thing that says when this model runs, make there be a circle that grows in radius over time. That ain't gonna be. It's not say that there's this thin meniscus of infected individuals inside a largely recovered population, and they're surrounded by a sea of susceptibles. You're not going to find that anywhere in the model. You're not going to find descriptions of these ridges anywhere in the model either. That's not, as I said, when we specify these models, we don't specify the behavior over time as a formula, as an expression. What we specify instead are aspects of a theory of, given the current state of things, how do things change? Maybe I'll continue this running while we're talking here. Instead, what we're doing is we're specifying a sort of theory of how things work. People are located in this lattice, and that lattice allows them to send messages to north, south, east, and west. And they progress in a certain way, and in fact, as Kimmelpreet earlier had said, we end up going and lending greater precision to this. So specifically, if you go look at the recovery transition here, what you'll find is that there's a quite precise foundation, and this thing is outputting information for informational purposes. Stop that for the moment so I can get back to this. I'm going to go look at recovery here, go look at properties for this transition. And what I'll find is, for example, that there's a certain rate at which they're recovering, a certain chance per unit time. for those from statistics or health background, this is a hazard, a chance per unit time of recovering, and that's specified by 1 over the average illness duration, and that's specified by a certain parameter associated with the main class. And so if we were to go and look, average illness duration has a certain value for this particular experiment, this particular scenario. So average illness duration here, for example, is 15, so 15 days of infection per person. Okay, they remain infectious for 15 days. So, you know, we have this kind of theory captured in this model that has to do with context and so on, about a particular individual, specifying how the behavior of a particular individual, you know, what happens over time, how do they change over time, change their states, for example, how do they send off infection messages. And that implies something. Not entirely obvious up front about the structure of the space that results. But in no way have we presupposed this pattern within the model. This pattern, ladies and gentlemen, is emergent. It's a higher level pattern that emerges from this model specification in a way that we don't, you know, immediately anticipate. So we could run this model out and allow it to run to completion here. And one of the things you'll find is that over time, this circle grows larger and larger. And what do you think the end outcome of this is going to be? What's the inevitable endpoint of what we see here?
Everyone recovered?
Everyone is going to be recovered. Let me ask this. So with everyone recovered, if we threw in a new infected, would it be the same thing? Would we see the whole thing again?
No.
Why not?
Because they're not susceptible.
Exactly. So it actually goes from an unstable state to a stable state. We'll be seeing this later in the class, this notion of states of a system as stable or unstable. Are they subject to perturbation? Do they just get knocked over by the slightest thing, like someone flies in with Ebola to the Saskatoon airport? Or are they stable? Are they resilient? Are they like a population that's been vaccinated very thoroughly against chickenpox, and someone could come in with chickenpox from Netherlands or with measles from the Netherlands, and it won't do any sort of disturbance in the amount of measles in town. It will peter out quickly. The notion of stability will be quite key to this. Here, we see a situation which is evolving over time, a different state, in fact, a stable state. And moreover, we see a certain speed at which it's proceeding. And in this case, this boundary will reach this sort of endpoint up here on the upper side, sometime around time 300, okay? I'm going to then close it. We're going to undertake some applications. Thank you, sir. Appreciate it. First of all, how long does it take to reach there? About 300. Now we're going to compare this with another situation. We're going to pose a counterfactual here. We're going to have this simulate a different situation, perhaps that we haven't observed in the real world, and see if we can understand the effects in that situation as well. Okay, so I stopped the model execution through this red button up here. Another alternative for doing that that's even more reliable is this button down here, the terminate button. Will terminate your screen that's located at just a so-called console here, which can be used to print out a message. Okay. Okay. So we're going to modify this model, and it may give a warning of sorts because we're modifying a built-in sample, and it may not be able to save it. That's fine. We're not going to do anything too deep here. Okay. So, ladies and gentlemen, I'd like to create. I had apparently succeeded, despite what I thought was impossible, against by saving a change to a sample model. I'm not sure how that happened, but I just deleted that, and I'm going to walk through this with you. So I'd like you to click on simulation here. simulation. This, or excuse me, it says simulation. That's an experiment, ladies and gentlemen. That depicts a scenario. It depicts a situation that we're going to be simulating, okay? And I'd like you to select copy on that by right-clicking and doing copy. Alternatively, for those who prefer the confines of the menu, you can select edit copy up here. Alternatively, you could go and you could do Control C and then Control V, or Command C, Command V on Mac. Okay, so I'll just do it with this right-click one, copy, and I'm then going to go up to the model as a whole and say paste. Okay, so paste. Here we go. Boom. Okay. So now we have this simulation 1, and we're going to have to fix it up so it knows about one thing. So we just pasted it. The screen should look like this. And you have to go to the General tab, and we're going to type in a new name. It's going to be called Slow Recovery. Okay. So for this particular experiment, this alternative experiment, as it were, we're going to have it proceed with a slow recovery. So select this new one and go down here into Properties. And you'll notice there's this Properties window. If you don't see it, you may want to do select the Properties from up here, from the View menu. Occasionally these windows shrink up, and then they sort of hide off here to the side. I'm just warning you about this. They hide down here, and you may need to restore them sometimes to their fulsome glory, and they'll come back. And so occasionally they're hidden. Okay. So what you'll do is you go to the General Properties, and for the name of this, make it Slow Recovery. And for the main object class, the root, so-called root, you'll select main. Okay. So this begins. Well, perhaps it began last time, but for those not from computer science background, perhaps this is the first sort of rude awakening to the fact that there's some strange terminology in computer science. We have strange jargon in computer science, and one of the points that may be unfamiliar to some people from outside of computer science here is the notion of root. What is root here? Why does it say root? In what sense, speak someone from computer science, in what sense is this guy sort of the root of the project? Can anyone sort of say? Why do we use that term root?
Entry point?
Sorry?
Entry point?
It's the entry point, it's the top level entry point below which other things sort of lie. So here we have sort of a main class, and that serves as the environment and sort of global stage on which various agents run. It doesn't have to be. We can actually have sub-environments like neighborhoods, which themselves have agents in them, and we'll probably be seeing that later in the class. But main is sort of at the heart of it, and it's sort of integrating together, coordinating some of these others. And so here we have sort of person under main, and we call this here root. Okay. So it's called the root, and in this case we just have to tell it, hey, which of these classes is the root one? And we say, hey, it's main. Okay, fine. Okay, now we're in great shape. But ladies and gentlemen, what do we have to do? We said slow recovery. So let me nuggetize that. So this should be